All right, welcome to the Friday Afternoon Physics Colloquium. So today's colloquium is going to consist of 5 talks from the Summer ATLAS and Fermilab students. And so I'll introduce each of the speakers as they come. So the first speaker is Valerie Buxbaum, and she's going to talk about outreach project for the summer of 2001 on the ATLAS experiment. Valerie?
Hi everyone, my name is Valerie Buxbaum, and I will be sharing with you the work I did this last summer at the ATLAS experiment. ATLAS is just one of many experiments at CERN in Geneva, Switzerland. CERN is the European Council for Nuclear Research. There's over 12,000 scientists from over 70 countries affiliated with this organization, and it's considered the largest science laboratory in the world. Some of the most notable achievements of CERN. Where does it point to?
Oh, I think you can just click on it. You don't have to point it anywhere.
Okay. So we have the W and Z boson discoveries that resulted in a Nobel Prize, the invention of the World Wide Web in 1989, the invention of particle detectors, most notably the multi-wire proportional chamber, also a Nobel Prize for that, and the very famous Higgs boson discovery in 2012 and the subsequent Nobel Prize for that. Now CERN houses the Large Hadron Collider. So what we're looking at here is an aerial view of the Large Hadron Collider crossing the border of France and Switzerland. You see the city of Geneva in the upper right, Lake Geneva in the upper left there. So what the LHC is a 27-kilometer ring of superconducting magnets and accelerating structures. And these, what we're doing is we're taking particles in opposite directions and speeding them up to 99.9999991% the speed of light. Then we smash them at collision points and see what comes out. So I worked on ATLAS, which is one of, ATLAS is one of 4 detectors on the ring. You can see it in the upper left there. The other 3 detectors are ATLAS on the right, CMS on the left, and LHCb up top there. So, and they track and identify particles. And on the right, the image you see there is the cavern. And these detectors and the LHC ring sits almost 100 meters below the ground. When we talk about ATLAS, we're not just talking about the people, we're talking about the detector too. So take a look at this detector. You see a human being there to give you an idea of size scale. It's the largest detector ever built in the world for it's 46 meters high, long and 25 meters in diameter. It measures billions of particle collisions a second. We analyze that data to identify and reconstruct particles, and we're looking for a wide range of physics, like the Higgs boson, but also out there things like extra dimensions and dark matter particles. And I'm really excited to share this with you guys because it's a new schematic that we've developed at ATLAS, and it's on display at the Visitor Center on campus there right now. So what we're looking at is 6 different subsystems that are wrapped concentrically in layers around the collision point. First, we've got our magnet system, and this bends the path of charged particles. Then we've got our calorimeters in the middle there, and that measures energies carried by neutral and charged particles. We've got our muon detector system, measuring the momentum of muons. And in the center there you see the itty-bitty inner detector, and that's where all the magic is happening. That's our collision points in the center there. Now, starting May of next year, we're going to start our run 3 after a 3-year shutdown for upgrades. Oh, there's one detector. So last week, we had our first proton beam injection into the LHC. This is to prepare for our next run starting in May. So this isn't for collisions, this is for tests to prepare for our full run. And what we're seeing here is our first beam slash events. And we're getting energy levels of 13.6 TeV, whereas from our last run we were at 13 TeV. So we're getting better energy levels from those upgrades we did over the last 3 years. Now the collaboration is the people, and it's really unique. It's a unique organization that all members participate in the decision-making and election and leadership. All work is shared, and it undergoes rigorous review before it's made public. There are over 5,000 scientists from 40 countries, and the U.S. has extensive involvement. There are 4 national labs: Argonne National Lab, Brookhaven, Lawrence Berkeley, and SLAC at Stanford. Many prestigious U.S. universities like Harvard, Yale, MIT, and the CSU system. We're NUPAC, the CSU Nuclear and Particle Physics Consortium, and all 19 campuses of the CSU system are eligible to work at ATLAS through NUPAC. Fresno State was the first in 2007. It was the only CSU involved in the Higgs boson discovery in 2012. thereby making it the first research a CSU was involved in that resulted in a Nobel Prize. So that's a pretty big deal. And as of this last summer, over 100 CSU students have worked at ATLAS. So what we see here is just a breakdown of the last 5 years, where the students came from, which campuses. You can see in 2020 there, none of us went because of COVID. And this year, 7 of us decided to work remotely, and 5 decided to wait to work in person next summer. Now, I worked on the education and outreach team. Why would an international lab want to do education and outreach? We want to inspire the next generation of scientists. And by doing this, we gain essential communication skills, we foster scientific literacy, and more important, we combat this other global pandemic we have of mistrust in science. And we encourage the support of our basic research. And I put up 4 examples of projects my colleagues have been working on. The first on the upper left there is the ATLAS Lego model. It's a meter long. It was developed by my mentor, /House. We have the Zooniverse particle search on the upper right there. If you're familiar with Zooniverse, it's a platform that has a lot of scientific applications. You can search for galaxies. There are biological applications. It's open to anybody. So anybody can go be a particle physicist. We have seasonal activities, like my colleague Mariana developed these pumpkin carving stencils for last Halloween. And Atlas Craft, it's a Minecraft world that is just the Atlas detector and the cavern and the elevators and really boring offices and things. So specifically what I worked on at the outreach team was educational principles. So these are things like coloring books at our most basic level, activity sheets, and we get more advanced, we have fact sheets, and our most advanced printables are cheat sheets. And the information is better understood when we present it this way. It's really visually appealing, and it's accessible to public of all ages. So we have the coloring books that kids can, well, I guess grown-ups can too. I like coloring books. And it's especially useful for teachers and students in the classroom, and more importantly, it's COVID safe. Now, what I worked on specifically were cheat sheets. Let's take a look at these. These are our most advanced educational printables. Here's an example of 3 we have public right now: conservation laws, the standard model, and Feynman diagrams. Now, these are one-page resource sheets that are designed to make ATLAS's more scientific material digestible to a wider audience. We provide definitions of common particle physics terms, and we give more detail than a glossary, but certainly less than a textbook. And these are designed to be understood by someone who is interested in particle physics, but not necessarily an expert. It's ideal, like I said, for teachers and students of particle physics. We print these out for use as posters or handouts. And like I said, this is a really new project. We just are developing it this year. We have a link for the 3 public ones, and I'm going to show you ones that are not public. They're blurred out because they're not public yet. But if you have a CERN account, I know many of you in this room do, you can take a look at signal and background, cross-section and luminosity, and make comments on the CERN document server if you would like. And as part of that collaborative effort I was saying is that everybody has a say in what's going on. And the last one I'm working on is the ATLAS coordinate system, which isn't public, but I learned a lot about pseudo-rapidity. We can talk about that later. If you want to know about pseudo-rapidity, the significance of doing this work. Like I said, it was a really unique work environment and an international collaboration. I didn't feel like I had a boss. I had mentors, for sure. I worked remotely with postdocs and PhD students, and I had meetings almost every day. Sometimes I'd have to wake up at 4 in the morning because of the time change. I was offered, I gave a talk at ATLAS Week, which is a quarterly meeting at ATLAS where different groups working can present updates on what they're working on. And I've been assigned the next talk or poster presentation for our educational printable team. I did a lot of research on complicated particle physics concepts that I was not familiar with before, and I was surprised by that. Oh, let me go back to that, sorry. I didn't just learn physics, this is an important piece. I learned graphic design, which is not something I thought I was going to learn at CERN, but I gained this really useful new skill set, and I fine-tuned my technical writing with help from my mentors as well. I got paid. NSF IRES award. I had a $4,000 stipend just for working remotely. And this year, if we go in person, I'll receive an additional $1,500 for travel. I established really meaningful professional relationships with my mentors. I now have references and connections for my future. And I've been invited to return next summer. And that's important because that means I represented CSU well enough that they will consider CSU students in the future. And these were supposed to come up before. This is a slide from the presentation I did at ATLAS Week, and it's just website analytics to show what kind of traffic we're getting on the material that we're making. And this is an example of the poster I'm making, and it's also blurred out. because it's not public yet, for the next time I will get to present. I would like to thank my mentors, most of all Sasha, Rebecca, Katarina, and Elise. They were so supportive with me working remotely in California, a completely opposite side of the world. I would like to thank my advisor, Dr. Gao, for just the support of the last 2 years. It's been tremendous. And thank you all for being here today.
Thanks for a great talk. Actually, so let's do like one question now, and then at the end we'll have general questions. So one question now for each student, and then at the end we'll open it up for general questions. So does anyone have a question?
I got a bunch, so somebody else go first.
What is pseudo-rapidity?
Pseudo-rapidity is a new coordinate that we use to identify where particles are, and we use that coordinate specifically because there are special relativistic effects, like time dilation and length contraction, that we have to take into account when we're looking at these particles going so close to the speed of light. So it's just a new coordinate that we use, and it's unique to particle physics. Thanks, Will.
Okay, well, so thanks again, Valerie. So our next speaker is Will Barden, and actually he's going to be followed with Gabriel Soto. This is actually a new direction for the particle physics program here. They're going to talk about work that they did on Fermilab on neutrino experiments, and it's basically neutrinos and Fermilab's neutrino experiment with DOE support. So Will, take it away.
Hi everyone, as Doug said, my name is Will Barden. I'm a physics senior here at Fresno State, and over the summer, my colleague and I, Gabe, we worked at Fermilab with Department of Energy support. We both received a grant and stipend to work with Fermilab remotely. It was through the visiting faculty program. Our faculty mentor was Dr. Gao, and our research sponsor was Dr. Minerva Betancourt. So some background real quick. What exactly is Fermilab? Generally, we hear a lot of talk about CERN, going to the Large Hadron Collider. Prior to the Large Hadron Collider being a thing, Fermilab was the particle frontier of the world. Their Tevatron particle accelerator is world-renowned. It is currently the frontier for neutrino research, and is actually responsible for some important discoveries, such as the top and bottom quarks. It was the energy frontier for over 30 years. Now, with the activation of the Large Hadron Collider in 2009, they switched to neutrino-only beams. They can actually reach those lower energy levels that are really, really hard to detect. And that's one of the projects that we worked on using the new ICARUS detector. So here you can have this little image of the particle accelerator, where we have a proton anti-proton beam, and a couple of detectors here. There's CVF and D0. And here is a diagram of a top quark interaction, which invariably produces also a bottom quark as well. So you can see the particle decays here are fairly complex, and things are a little bit messy. We'll try to clean those up for you and clear a few things up as well. So there we go. So what exactly are neutrinos? Everyone's familiar with protons, electrons, and neutrons. Neutrino sounds a little bit weird. Its name is just Latin for little neutral one. It's like a neutron, just really, 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 really small. They're absurdly lightweight. They're a fundamental particle, meaning that they don't decay into yet more particles. You smash a couple protons together, you can get different kinds of quarks, you can get different interactions. Neutrinos themselves are basically the end result of any interaction. You don't get anything more from neutrinos. Now, they come in 3 different flavors. They're leptons. So here we have the lepton generations. You have our favorite, our 3 generations of quarks. You have top, bottom, charm, strange, up, down. Then you have our more familiar things like electrons, and then also the muon and the tau. And then you have their neutrino counterparts. So tau neutrinos are produced from tau interactions, muon neutrinos from muon interactions, and the electron neutrino from electron interactions. And those constitute our 3 flavors of neutrino that have been discovered thus far. Now, the weird thing about neutrinos is that as they fly through space, and for instance, billions and billions and billions of neutrinos are produced every second in the heart of the sun, and in fact there's billions and billions of them passing through us right now, they change flavor spontaneously. It's called neutrino oscillation. We don't really understand it. So an electron neutrino can become a muon neutrino, can become a tau neutrino, and back and forth, and we don't know why. So the working theory is that there is a 4th unknown type of neutrino called a sterile neutrino. And that's what mediates this weird oscillation. So going back, that's what the neutrino program is kind of working on right now and has been for the past several years. The tevatron, which you saw a couple slides ago, produces a very intense particle beam, which on this diagram sweeps from right to left, going this way, and then passes through a couple different things. So right here, we have there's a steel plate, and the particle beam is designed in such a way as to produce mu1 neutrinos only. The interaction that they have is designed to produce only mu1 neutrinos. Then passes through microboom, which is an existing detector, mini boom, and then their newly installed ICARUS detector, which has 760 tons of liquid argon, and that is really awesome stuff. It has a low activation energy, makes it really easy to see low energy particles down to the mega electron volts. And then the mu1 neutrino beam just continues on through the surface of the Earth. So you can see the beam originates pretty far over here and then goes about 1 kilometer or so before it hits ICARUS. So right now ICARUS acts as what's called the far detector. We can see, we can get like kind of, detections from these other detectors before it hits ICARUS, and then you can see how the beam evolves along the length of the beam line. Now, ICARUS itself currently serves as the far detector, kind of getting a census of the end of the beam, but the beam does continue on through the surface of the Earth. As the experiment continues on in the coming years, detectors at Stanford will actually serve as the far detector, and ICARUS will become the, relatively speaking, near detector.
Oh my God.
So there's about 800 kilometers distance, and so by basically measuring the beam here on the near side, near where the beam originates, and then measuring it again after it passes through a good chunk of the surface of the Earth, if there's anything other than muon neutrinos in the beam, then we'll basically have caught them in the act of oscillating. And if there's, say, more electron neutrinos than there are tau neutrinos, we'll see that there's a preference, there's a bias of some sort, and that can kind of give us clues into the behavior of these neutrinos and how they oscillate, and possibly maybe even a sterile neutrino somehow. Because any changes must have been happening en route. Now, our work is kind of special because we have to make sure that the detector actually works. Most neutrino detectors are buried deep, deep underground in mine shafts to shield them from cosmic rays. High energy particles that strike the surface of the upper portions of the Earth's atmosphere and then cascade down just this whole shower of charged particles. It's like a naturally occurring particle accelerator, like a large hadron collider in the sky. All these charged particles are ultra high energy. You can see right here what one of these particle cascades might look like, where you have a high energy incident particle, maybe a proton or something from the sun, and then that strikes, say, an unfortunate oxygen atom in the ozone layer, and then it produces neutrons, pions, muons, mu neutrinos, electron neutrinos, positrons, all over the place. And that can interfere with electronics here on the surface of the Earth. Elections have been upset because the computers miscounted votes due to cosmic ray strikes hitting the memory channel inside of a computer in Prague somewhere. So we need to make sure that we can actually account for this in the data so that it can be properly ignored. So here you can see how what a standard neutrino detector looks like. This is in Japan. It's in the bottom of a mine shaft. Normally this is filled with distilled water, and all these little bubble chambers are the actual detectors. And here you can see, this is an image from the late 50s. This is the very first detection of a neutrino, where you have this long, thin trail where normally a charged particle passing through a bubble chamber, it leaves a trail of ionization, which is then visible, but something happened here where there's nothing leading into it, it just spontaneously happened. And that's because a neutrino struck an atom, which resulted in the release of energy and the release of charged particles, including, I believe there's some beta decay here, so this was an electron neutrino, I believe. Now, neutrinos themselves, as I said earlier, ultra lightweight, very, very, very lightweight. Their mass is less than 2.14 times 10 to the negative 37 kilograms. So that's 0 point and then like 37 zeros, 214 kilograms. They're absurdly lightweight, unlike myself. And here we have our cool little sterile neutrinos just zipping on by, completely unfazed by everything else around them, because they're awesome. Now, ICARUS itself, as you saw in the diagram earlier, that little map, is not located in a mine shaft. It's relatively close to the surface of the Earth. Cosmic rays are a problem, hence the need to account for them through a cosmic ray tagger, which is what we worked on. So the detector wall was specially designed because it has both interior and exterior sensors. It has an outer wall and an inner wall, kind of like a double hole design like the Titanic, but without the worry for icebergs. So a cosmic ray that wants to interfere with the experiment would have to pass through both before it can interfere. So by virtue of like having it hit the outer detector before the inner detector, and then using time of flight calculations, we can actually determine, oh, a cosmic ray entered the experiment here, and then actually passed through at this angle, this time, at this rate of speed, and that produced this particular hit. We can ignore that. It can be properly subtracted from the data after we reconstruct the flight path. And right now, ICARUS, they just got a new detector wall. Everything is being installed. And we're working on, we worked with Dr. Minerva Betancourt through the visiting faculty program to look at first run data from ICARUS. They're firing beams into it for the very first time. We got to look at the very first data sets, and we analyzed a ton of them. And we were able to produce workable results, workable analyses for the calibration of the cosmic ray tagger. And for that, I'm going to pass the laser off to my colleague Gabe, who's actually going to go more into depth into what our work actually consisted of. Gabe?
Thank you, Will.
Thanks, Will. So take it away, Gabe.
Yeah, I'd like to thank everybody for coming. I need support. My therapist said that. So this will be good for me. Okay, so Will kind of gave us a good understanding of what we're looking at, but I'm going to give a little bit more detailed understanding of what the ICARUS detector is. And like he said, it's a liquid argon detector, and there's a cosmic ray tagger embedded into it, and its purpose is to shield the incoming cosmic rays from being integrated into the collider data. So there were 6 subsections of the detector that we worked on, and each subsection was divided into 32 channels with 82 front-end wards each. So on the bottom you can see there's a cartoon of the detector itself right there. And there's the top layers, and then there's the, I don't know if you guys can kind of see it, the inside layers right there. That's the majority of the ones we worked on. So the cosmic ray tagger, Will already kind of explained this, where the cosmic rays come and they interfere with the outer wall, and then they hit on the inner wall, and then we can kind of remove that from the collider data. And we say, okay, so since we know that it came out from the outer wall and inner wall, we can remove that from our data that we've already taken. So that cartoon's a very good representation of it, of what the cosmic ray tagger does. So some skills that we had to learn for working at Fermilab was, one, we needed to know C++. Second, root, because it's kind of an extension of C++. They're both like object-oriented code. And we had to have a fine understanding of Linux, which is an operating system used to run, compile, and create code via command line. We also used a little bit of SAMWeb, which was used to search databases for files. So that came in handy when looking for different types of root files that we wanted to analyze. And they also supported us with our own email, and we were able to access their servers on our own laptops and computers. So the units of measurement that will be important for us, that was important for us, was ADC, and it stands for analog to digital counts. So what happens is when a photon interacts with the detector, it causes a current, and the current is measured and converted into a signal, into a digital signal. And this signal, we'll see this later, it's plotted as a photo peak for each hit. And on the right here, we have an image of the inside of the detector. So there are 4 different types of data that we plotted. So this bottom left is a spectrofit, and this is probably the most basic one because it gives us the ADC of each hit. So on the bottom we have the number. Oh, I'm sorry. On the top we have the number of hits, and then on the bottom it's the different number of ADC. And so when we're getting the different amount of hits throughout the experiment, we get accumulation in certain areas. And so at certain peaks, we are able to count them, and then we'll be able to use them, plot them on a linear fit, which is on the top right here. And the y-intercept for that linear fit is, we get that from the gain fit. And the gain fit is basically a measure of all the electrical noise that we get from the experiment. And then from this linear fit, we're able to get this, the gain fit, we're able to get this pedestal fit, which is a representation of the gain fit and noise that is accumulated throughout the experiment. So the ideal data for the 4 different types of plots is, one, for the pedestal fits, we want a symmetric histogram, and then we want low noise and a clear peak. For the spectra fit, we want low noise, obviously, and then we want a clear identifiable peak. If there's not clear identifiable peak, our pedestal fit will look like very wonky, and it'll mess up the linear fit, and then it just kind of snowballs. And then the gain fit, we usually want it to be concentrated in a certain area. For us, we wanted it to be around 65, but usually it was around 55 to 60 ADC. And the reason why we want it to be in that range is to ensure consistency in the amount of noise throughout each run. So the importance of the fits is to show the practicality of the data. It reveals correlation trends and data collection from the data collected of the detector, and it provides feedback of possible issues. And overall, it shows how well the experiment is performed and where. So this little plot, well, not little, it's big, huh? This big plot, Will came up with this. Well, we both worked on it, but he had this great idea of, instead of looking at every individual pedestal fit, we can look at the average pedestal fit within each channel. And the reason why we did that is because there are 32 channels and 80 front-end boards. So each channel had 80 front-end boards. And we averaged at the end of the internship of looking about 500,000 histograms. So, you know, describing every histogram was a little bit of an issue when you're trying to, present it to a group of scientists. So yeah, so this would reveal where the trends were at, you know, where on the detector was the data, or the detector was, you know, providing bad data and good data. And that's represented with the green on the plot. So the green means a good Gaussian fit. The yellow means broad, so we got a broad fit that's not ideal. And then orange was asymmetric. And it was very helpful for figuring out which parts of the detector were working and which ones were not. And then on the top, these are different thresholds of ADC that we ran through the detector. So what we found from analyzing the data were both the west and east sides of the detector had the most promising results. When the machine was ran for longer intervals, there was better statistics, along with when we halved the bins in the histograms, there seemed to be better statistics as well. The threshold 280C had the best results in data, and these, oh, I'm sorry, I skipped some. When we halved the intervals, and when we ran the machine for longer intervals and halved the amount of bins, we got clear peaks and smoother histograms, which led to better linear fits. So the results of the internship, first of all, we worked remotely with, on a daily basis with physicists and PhD students and postdocs. We learned new methods of experiment and critical thinking. We gained a good relationship with Dr. Minerva and gained a positive reputation with Fermilab. we also worked on a daily basis, 40 hours a week, and we also we both gave talks throughout the entire internship, which was nerve-wracking. So yeah, that's all I say about that. We were also paid $600 a week, total of $6,000. And we were invited back for the next summer, and we might be able to travel there, and they will provide us with housing. And our mentor, Minerva, offered us letters of recommendation from schools like Chicago, MIT, and then Minnesota and Iowa.
Fantastic.
And that's the end of our presentation.
Okay, a fantastic talk. Excited to learn more about neutrinos. So 2 speakers, 2 questions. Fred?
I was going to ask, was it in Iowa where Baryon wound up?
Yes.
Yes, and he got his PhD, finished.
Yep.
But actually, what I wanted to ask Gabriel was, to use Linux here on campus, and what support is available?
I only really use Linux for this, and then when I was doing a class 175T, which was like the tools for CERN, and you said applications that you support?
Yeah, the reason I ask is that is Linux support on campus here as skimpy as it used to be, or have they improved it?
We don't know, but students in the group, they have Thor accounts. We use the...
A lot of the, me personally figuring out Linux was just searching up sources on the internet.
Yeah, I ask because if we want our students to be involved in real scientific research, I wish this campus had some kind of support for Linux. When I came to Fresno State, I was bearing a Linux box bought with my Hubble Space Telescope grant, and when the person came along to attach it to the internet, I was told, oh, I only do Windows or Macs, I don't do weird ones. And well, this is a computer, a copy of a computer that is on every desk at Space Telescope Science Institute.
Well, no,
I really wish this campus had some support for
no,
it.
they're just saying, welcome to Fresno State. This is the expectation. Just a joke. I love my job. No, actually, I had a question for Will. And so now you get the ICARUS is going to be focused on neutrino experiments, right?
Yep.
So they've already started taking data.
Yes.
Right? And so what is it that they hope to get out of this? Is it to figure out the number of neutrinos? Are there 4? The sterile one? So what are they trying to get?
The ultimate goal is to have conclusive evidence of the existence of a sterile neutrino. There is a recent article, and by recent I mean it was published the day before I gave my talk at APS a couple weeks ago, from SBND, which were actually negative results for the existence of a sterile neutrino. That's kind of thrown the wrenches into the works. I am not super familiar with the results. I'm still reading through and processing. But that is the end goal. It's basically a hunt for the sterile neutrino. Okay. And largely that's just through broad aerial view, doing population counts of the neutrinos along the beamline when they fired from Chicago to Stanford, and using near-infrared detectors.
Okay, great. And you were going to say something before I interrupted you.
Yes, I work after school. It's my little after-school job at the Technology Service Desk. We do have a support documentation for Linux. I wrote a good chunk of it myself.
Okay.
So if you need to enter Rome, I can help you out.
Okay. One thing I wanted to ask was, okay, an electron neutrino corresponds to an electron. A muon neutrino corresponds to a muon. A tau neutrino corresponds to a tau lepton. What particle does a sterile neutrino correspond to?
That's what makes it sterile. It corresponds just to the neutrinos themselves and would seem to serve only as an intermediary as they oscillate from electron to muon to tau neutrino, seemingly spontaneously. It would serve state of being for the neutrinos as they transmogrify from one flavor to the next. Beyond that, I don't really know the properties. It's still entirely theoretical.
So,
Wait, we'll do questions at the end, but, so I was kind of I don't want to say a jerk, but I was like, very, like, let's stick to the time. And you guys have been doing beautiful, so if I have offended you in saying stick to time, I apologize. But, Gabe, Will, once again. So our next speaker is Dan Brown. Let me just say he just finished his master's degree, so you can call him Master Dan. He's going to tell us about search for VBF Higgs boson pair production in the BB TauTau final state with ATLAS experiment at LHC at CERN. Dan, take it away.
Thank you. So again, I'm Dan. So this is what my master's thesis was on and the current research I've been doing. So a little bit about me. I grew up in Fresno, got my bachelor's degree here in physics 2014. Then went on to get my teaching credentials through Cal Poly in San Luis Obispo. Taught high school physics and chemistry for a couple of years before returning to Fresno State for the master's program. You've already heard some stuff about CERN, so you know it's where the World Wide Web was initially created. You know it's where the Higgs boson was discovered, along with W and Z vector bosons. And here's the standard model. Just reflects, describes the three forces, fundamental forces: the electromagnetic force, the weak and strong force. Also classifies the elementary particles. I included graviton on there. It's not included in the standard model yet, but hopefully it will be sooner or later. But yeah, so gravity still has yet to join the standard model of elementary particles. On the right, you can see it's inside the LHC. There's a collision of the protons colliding together with such energy. This creates a cascade of different particles that are produced, and they decay out until we finally detect their final states in the ATLAS detector, which you see in the bottom portion there. Okay, so far the standard model actually has been very accurate in giving predictions that have been borne out by multiple experiments. Okay, so it's our best understanding of the universe thus far. So why even look beyond the standard model? Well, there's some things that it can't explain, such as dark matter. So dark matter, it's only detectable through gravitational interactions, okay? And it's still we're still unsure if there are, say, dark particles that exist, but there's something that the standard model can't quite explain it yet. And then we also have something called Baryon Asymmetry, where according to the standard model, our universe should have been brought about into equal parts of antimatter and matter, but we don't see that in our universe. There are some processes within the standard model that do produce more matter than antimatter, but it's not enough to actually account for what we're seeing in our own universe. So, since the standard model can't explain these, it must be incomplete. So this is more along my research, so the search for more Higgs. So the Higgs boson, newly discovered as we know, and it's already so rare. It's 1 in 1 billion collisions where it's actually produced, and me searching for Di-Higgs or 2 Higgs bosons, it's even rarer than that. Okay, so some of the predictions about Higgs are just how often they are produced, and also what they decay into. So I'm specifically searching for that final state of BB TauTau, 2 B quarks, or we call them B jets, and 2 tau particles. Okay, so looking at the theory, according to the standard model, we're using Monte Carlo simulations to simulate these collisions at the LHC. Okay, so if data reflects the theory, so far so good. If it doesn't, then could be new physics. Might have to come up with a revised standard model. Okay, so maybe the particles actually don't get their mass the way we think they do through the Higgs field. And theoretically, the Di-Higgs can be produced through what's called vector boson fusion. Okay, so I want to work on how to identify the Di-Higgs that are produced through these Monte Carlo simulations, okay, and want to optimize the production of it. So that means I'm going through the signal of these Di-Higgs that are ending up in the BB TauTau final state. I want to keep the signal and get rid of these background events that are simulating other production mechanisms. Okay, so I worked with Adam Parker and Catherine Grimm out of CSU East Bay, and Mary Sylvia Donadelli out of University of Sao Paulo. And what we were working on was the vector boson fusion production mechanism. This is different than the more common gluon-gluon fusion production mechanism. In VBF, both taus will decay hadronically to produce these B jets, or jets. Okay, so I'm working on cutting and optimizing the signal of the vector boson fusion, get rid of as much background as possible. Okay? And so one of the first things we were doing was just plotting and examining different variables to find different thresholds to be able to cut out more of the background and keep more of the signal. Okay? Another thing we started working on initially was the separation between the gluon-gluon fusion and the vector boson fusion. Okay? There's already a dedicated analysis to the gluon-gluon fusion. Something else we were looking at through the vector boson fusion was this C2B coupling. So that's a parameter that if you vary it, it's normalized to 1 for the standard model, but if we vary it to be increased or decreased, that changes kind of the probability of the Di-Higgs actually being produced. Okay? And I worked with mainly Python and C++ for all my programming needs. Okay, so I was working with the Monte Carlo data set that simulates the LHC, analyzing different variables such as momenta, different angles, masses, or energies. Okay? And I'm comparing background events, which simulate other production mechanisms that we're not interested in right now. And so we want to cut out events that are not the decay we're looking for. So if it ends up that an event has particles with the momentums, angles, etc., which match the theory of the decay we're looking for, okay, so that BB TauTau final state I'm looking for, that means we may have found that event. But again, there's always uncertainty. So far my research has not included the uncertainty and other systematics like systematic error and so forth. So on the right, you can see the Feynman diagram for general vector boson fusion occurring. We see the 2 quarks coming in, radiating off a vector boson, either W or Z bosons. And then where the coupling is, that C2D, that's where they produce those Di-Higgs, the 2 Higgs bosons. And then those will go on to decay into the 2 B jets and the 2 tau particles. But one of the things I wanted to point out was, so when the quarks actually radiate off these vector bosons, they're losing energy initially. So we'd expect these quarks that are the same thing as the 2 extra jets that we see in the detector. These quarks should have a higher angle because they radiate off some of the energy. So that was in particular, that was one of the variables that we were more interested in than the others. Okay? And it's pretty hard because there's a lot of events. Okay? Here's a collision inside a detector. So you can see we have the collision happening at the center there, and then through reconstruction, able to figure out that, oh, it was an electron that was in the final state along with a muon and 2 VTAG jets. Okay? So it can get very, very complicated and convoluted in these events. Okay, so these are a couple of plots that I ended up producing. Okay? The first one is a background rejection versus signal efficiency. Okay, we can see from this plot, it looks like one of the more optimizations of our vector boson fusion, we can actually keep about 80% of our signal while rejecting almost around 95% of the background, which is really good. We're on the right track. And again, for this BDT response, it's a boosted decision tree. So what this, running our Monte Carlo simulations through this, what it does is it goes through each event kind of one by one, looking at all the different variables and deciding whether it's definitely an event or definitely a signal or a background event. Okay, so in the blues, definitely signal, the red, definitely background, and then right in the middle there, it was not too sure. Couldn't decide one way or the other. But what we do see, what we can take away from this is that there is a good separation between our signal and background. Okay, and here's, let's see, this was running through a limit setting framework called T-Rex Spitter. Okay, so these are pre-fit and post-fit plots. I made these for a lot of different variables. This one is the variable of Di-Higgs, or the mass of the Di-Higgs. Okay, and in the pre-fit plot, we can see it's actually matching up pretty well, the data versus the predictions. Okay, and then in the post-fit plots, we can see it's matching up even better. Okay, specifically like in between that range of 200 to 800 GeV. Okay, so again, on the right track, it seems to be staying within the standard model. Okay, so in summary, background rejection versus signal efficiency and BDG response. It was presented to the SLAC ATLAS group meeting last year. All these results were also presented to the APS Far West section last year and this year. And the preliminary studies on the fitting procedure were presented to the ATLAS working group using the input variables for that final state of BB tau tau. That was presented earlier this month, and this was the last two plots that I showed you here. Okay. And so far, the data is fitting within the standard model. And again, this is very preliminary. Still need to work on other settings to include the programming framework, such as like uncertainties and other systematics. And this is my master's thesis, as Dr. Singleton already told you, and has been approved and submitted to graduate studies again earlier this month. My plans for the future, I'll continue at Fresno State next semester as a lecturer. I look forward to it. And in the meantime, I'll be looking for teaching positions at community colleges and junior colleges. And that's it for me.
Thanks a lot. Thanks a lot, Dan. Great talk. Again, one question.
Hi, so you said you worked with both C++ and Python. What was the application of one over the other in your research?
So as far as I could tell, like I really enjoyed working with Python. It was a lot simpler, and those were that's when I was actually making a lot of the programs for making plots and different stuff like that. The C++, I was mainly using that when I was adapting other people's code to be able to work with the variables and all the data that I was working with.
Yeah.
So that was like the main difference with me.
Yeah, I was kind of expecting that you would be personally working with Python, since it's
Yeah.
a lot easier to implement new code in Python.
Mm.
That's good to know, and I think that falls in line with what I was discussing.
Okay.
Okay. So I have a question for you, but I'll wait till
Oh.
the end. Okay. So thanks, Dan. Noraim?
Sounds good.
Okay. So just so Noraim is also going to talk about the work that she did on the ATLAS project, a search for resonant Di-Higgs production in vector boson fusion. And so this is going to be similar to what Dan did, but Noraim is going to be looking for BB to photon-photon. So Noraim, take it away.
Yeah, I'm seeing. Okay. Good evening, everyone. My name is Nunez, and I'll be giving a talk about my research project for my thesis. So my study focuses on the search for resonant Di-Higgs in VDF production. But I'm going to break down the jargon so throughout the presentation. I do my collaborative work with the ATLAS group at CERN, located in Switzerland, and the data I use for my analysis comes from the ATLAS Detector, which is a subgroup of the Large Hadron Collider. So here we see the general internal structure of the ATLAS detector. The diagrams on the right side help picture the nature of particles in space and how the detector mimics that same behavior. In the detector, there's different sectors or sections that capture different information based on the life expectancy of these particles. Like if you look at the electromagnetic calorimeter, there's muons and electrons that decay. And You can imagine the detector as a giant 3D camera where we take pictures in 3D of each collision that happens, and then we look at the details of those pictures to understand what's happening. So by using this technique and the theoretical structure of the standard model, this helps identify what types of particles are out there. So the Higgs boson is a fundamental particle associated with its own field, and it gives some form of mass to other particles in the standard model. In 2012, the Higgs boson was discovered by the ATLAS group. This was theoretically expected and described by the standard model, which also confirmed the 1964 Higgs theory. So great. We found the Higgs, but now we want to study more of its properties. And one of the theoretical properties is that the Higgs can be potentially produced in pairs. Two Higgs right here. Now we believe the paired Higgs will fit in the beyond standard model that Dan had mentioned, which basically explains phenomena that goes a little bit more in depth than the standard model can explain. Therefore, my focus will be on the paired Higgs, specifically made up of 2 photons and 2 quantum quarks. So here we have the Feynman diagram that models the fundamental structure for the properties of a paired Higgs under vector boson fusion, VBF. VBF occurs when a quark from the Large Hadron Collider radiates a heavy boson, so the quark here, the boson here, the heavy boson, and interacts and fuses to produce a particle like the Higgs particle. And this is a very specific type of process that I'm going to be focusing on heavily throughout this study, okay? So I'll be mentioning the term VBF quite often. And it has been observed that a VBF can produce a single Higgs boson, that's true. But the question here is whether there is a particle X that produces paired Higgs under VBF. And if particle X does exist, it must couple with the vector bosons, and it must couple with the Higgs. And that would also imply that particle X is at least twice as heavy as the Higgs. So I have to work backwards, starting with collecting data from 2 photons and 2 bottom quarks to ultimately get 2 Higgses, and then reconstruct the 2 Higgses and see if I can get any particle. So if particle X does exist, what do we expect to see? And this leads to the goal for the study, where we have the 2 plots of the 2018 reconstructed Di-Higgs, given the same final state that I'm working with, 2 photons, 2 bottom quarks. And the process here, in the x-axis, we have the total mass or the invariant mass of the Di-Higgs at different mass points, okay? And the y-axis, usually it's always the number of events. Oh, and whenever you see pre-selection, post-selection, pre-selection is no cuts, post-selection is I've applied cuts, so now I have a little bit less data. And the colorful peaks are they're signals at different mass points, and they're made up of resonant Di-Higgs particles, which basically means peaks of energies that comes from 2 Higgs. Each signal mass point represents a different hypothesis for what particle X can be. So this gives us a clear idea of what to expect if there is a particle X at one of these mass points. The black peak is the background, and that's made up of random pairs of jets and photons. Jets are bottom quarks, okay? The challenge here is that we want to increase the signal and decrease the background, and having a strong signal can mean we could find more particles, but getting rid of too much background can affect the number of events. So we want to keep enough events to get promising results. And applying cuts can get a little bit tricky. So I want to collect the 2 best photons and the 2 best bottom quarks, okay? So I apply a cut that says I only want exactly paired photons, which is this part here. And to confirm that I have a strong selection of photons, I reconstructed a set of paired photons, which results in a strong peak here. I took one more step forward in applying another cut to only maintain the range of interest of the peak, which is a pretty good sign. So I have the signal above the background, which is also good. And if you look at the mass on the x-axis, you see the peak is at 125 GeV, which is consistent with the Higgs mass. So that confirms that we have strong paired photons. Excuse me. The diagram here shows the general principle of identifying B jets based on their trajectory inside the detector. Bottom quarks don't decay until the second vertex. And all that occurs in the interval B layer, which is in here. That's the IBL, which basically is designed to trace back the trajectory of B jets. And since B jets, or bottom quark jets, are very heavy in decay at the second vertex, it also creates a higher transverse momentum, which is really good for us. B jets, they are generally hard to detect, so the ATLAS group specifically designed algorithms to tag these bottom quarks just for future runs. And let me point out that if you reconstruct the bottom quark jets, you would also get a high peak at the Higgs mass of 125 GeV, just like the paired photons. So here I have two bins. The first bin 0 to 1 is not tagged, and then bins 1 to 2 is tagged. I applied a cut that says I only want the tagged jets, which results in this graph here. So that's good. Here I have the VBF jets. So these variables already existed for me, and we have the mass of the dijet system, which is in purple, given the diagram here as well. We have jet 1, jet 2 in VBF. And we also have the change of pseudo-rapidity, which basically means how far apart the angle of two jets are, which is also shown in the diagram right here. So delta eta, distance between the two jets. Here are the borders as well. The green borders correlate with this change of rapidity, and this is before the cuts and after the cuts to get rid of the background here. Same thing for the mass. So this is where it gets really interesting, because now we're looking at elementary stages for conducting physics. This leads to my current contribution to the analysis, where I have created like new variables or object variables that correspond to some jets in VBF. And using the properties of the Lorentz vectors like mass, energy, the angle, transverse momentum, etc. I went along and chose the transverse momentum, and I compared it with the signal mass points and the background. So the main idea here is to see if there's any correlation between the signal and the background. If the background is larger than the signal and the shapes are very different, that implies there's no correlation, which is exactly what we want. It's easier to see it on mass point 800, where you see the signal all the way at the bottom. Okay. The second step is to create a 2D plot where my pre-existing variable, like my dijet mass in VBF, is on the x-axis, right here. And the new variable that I chose for the transverse momentum is on the y-axis. And if there is correlation between the two variables, you'll see a huge diagonal line. It will be like centered here. And it will be a space between the top and the bottom. And that will show that they are correlated, but that's not useful to us. If there is no correlation, which you see right here in the diagrams, that means that the new variable could be potentially useful. And the next step would be to go back, apply cuts to get rid of more background, and then compare the variables again. So we identified a variable that might be interesting to look at, being the transverse momentum. I'm going to take the signal and divide it by the background so I can then compare the before and after cuts. And hopefully my new cut will improve the overall quality of the signal, which is the signal efficiency. My goal is to increase the quality by 10%. So for my results, I looked for new variables. I'm currently using the transverse momentum of that object that I created myself. And I've been applying cuts to increase the signal. I will be comparing the signal and background predictions to raw data, but now I'm using simulations. And hopefully it'll support any findings for a peak at one of those mass points or what could be particle X, and that would also influence new window of possible theories. So in summary, I began my analysis last year, and I'll be presenting this to the group either next month or in January, or I'll also be giving upcoming talks at upcoming conferences. And I'm expected to graduate next semester and hopefully start a PhD program after.
Okay, so question for Noraim. And then actually, can all the ATLAS students, can you guys kind of line up behind here? Because then afterwards, and I think they can see you there, but so questions for Noraim though. Okay, so actually, Noraim, so I have one. So what, is there any like idea what this X particle should be? Or is it? Okay, so Valerie also had the same question. She had this, so what's the X particle? Is there?
Well, we think that it could be a graviton. That's what we're leaning towards, but we're really not sure.
But so it could be a graviton.
Yeah.
Okay. Ask away, Fred.
Noraim, a graviton, wouldn't that imply a close link with quantum gravity? This would be a big deal.
Yeah, so probably it's not a conventional graviton because it has mass. So the conventional graviton is going to be massless, right? But there are various theories where there's like some form of the graviton that basically has mass, and I guess this would be it. The theories would have to be exotic because normally quantum gravity effects don't come in until like super high energies like the Planck scale.
Yes.
Right? And so if you see evidence for some flavor of graviton at this energy scale, that means you have something like a large extra dimension model, right? So in the large extra dimension models of Orkani, Hamed, Diwali, and Dimopoulos, basically gravity becomes quantum already at the TeV scale, right? So that could be one possible model for this. But yeah, it would be if that is the graviton or some cousin to the graviton, that would be super exciting.
Yes, it would be like finding a transistor radio in an archaeological site for Neanderthal. You know, something that completely changes everything.
Well, actually, the ATLAS students, they all liked your analogy. It was good. So, okay. So, any other questions for the Fred? More questions? Any questions? Oh.
What class have you lectured?
Oh. Well, I'm down for what, 4B,
2A, 2B, 4A, 4B, 4C. No, we actually, right now, we haven't teaching a lot of classes, but I think officially it's 2A, 2B,
and 4B,
and 4B.
and then the
Natural
science
science
probably
116,
won't, might
but
not run,
But
depending on.
that one doesn't look like it's going to run. And then a lab. So, yeah.
What time? Because I take 4B next semester. I'm like, I might as well take it with you. So
I have no idea.
okay, I'm gonna try. I really like that lecture of yours.
But I think my name should be on there though, right?
Yeah, so
Yeah,
if you go to register,
yeah.
Dan Brown.
Okay. Hopefully it's still open. I mean, no, like it's not already filled up. I mean, you're fantastic.
Or not that I know of, but I don't know if we capped it yet or not.
Oh, yeah, actually, did we cap it?
Yeah, it's kept.
It is, okay, good. Okay. So actually, I have a non-scheduled question for Dan.
Perfect.
Yeah. So the fact that quarks make jets, like, I know. And so basically Noraim talked about photons in B. So the photons don't make jets. Now the leptons, right, the tau, so you're looking at those making jets.
No.
No?
No, those are just tau particles,
So
but there was the 2B jets specifically coming from the Higgs, the 2 taus also coming from the Higgs, but then there was the 2 extra jets that were left over from the initial quarks.
Oh,
That radiated the vector boson.
Okay, so the taus themselves are basically very clean signals then?
Right, yeah.
Okay, all right. But I thought you said something that the taus decay hadronically and make jets, or?
Well, wait, am I thinking about that wrong then? Because I'm pretty sure it's just the, like, 2B jets, the taus do decay hadronically. Does that mean they are jets if they decay hadronically every time?
Yes,
Yeah.
so-
Oh, okay, then, yeah, they are also jets,
So
yeah,
let's-
but not B jets.
They're not, okay, so that's it. So they do, so the taus do make jets when they decay like hadronically, which they have to. But so my question is, so can you distinguish those jets from like the B jets?
Right, yeah, so that's where, like, how Noraim was talking about the B-jet tagging that you do, so that's where they're determining if it's like the B-jet or not.
Or not? So you
Yeah.
can distinguish between the jets that come from the tau versus like the direct B jets?
The B jets is much
Yeah.
heavier.
Okay.
So that's
I'm
the-
pretty sure we do discern between the two, I'm not exactly sure how it
Okay.
happens, so.
Okay. Wait, Noraim, you wanted to say something?
Oh, I said yes.
Oh, okay, yes.
Oh.
Yeah.
All right. No, thanks, Dan.
Yeah.
Thanks. Other questions?
Why are sterile neutrinos called sterile neutrinos?
I guess you could just say it's supposed to be a neutral one, like it's supposed
I
to be
was-
that all of them can pass.
I was actually digging for that exact answer earlier, and I got way out into the weeds regarding neutrino isospin and chirality. Regarding most active neutrinos, tau, muon, electron, have a left-handed chirality. Their antimatter counterparts have a right-handed chirality, but they're not necessarily the same as the active neutrinos. It gets way out there. I'm not quite sure exactly how they landed on the name sterile. I had assumed that it just was based on the fact that they don't, they don't pair with other base leptons like the tau particle, muon, or electron, and the fact that they seem to be simply mediators of the neutrino oscillation phenomena, which itself is very, very poorly understood. And the only reason that's important is because it indicates that neutrinos have mass. The mass is so low that the only reason we know they have mass is because of the oscillation. If they were massless, they wouldn't experience time due to relativistic effects. And an electron neutrino would always be an electron neutrino because in order to transition from an electron to a muon neutrino or tau neutrino, it would have to experience some non-zero amount of time, which would mean that it travels slower than light, the speed of light, meaning it has mass. And somehow the sterile neutrino would be a very easy way to solve the mystery of how it does that.
Okay, you're not expecting to directly see sterile neutrinos. You're expecting to infer their presence from reactions that only they could involve.
Exactly.
Like quark, just like with quarks.
Yep. You never see quarks by themselves. Quarks always exist as triplets and protons, neutrons, and other baryons.
Yeah. You try to knock a quark out of a proton or a neutron, and it will take so much energy you cannot help but create other quarks.
Yeah.
So it's like being a kid with bubble gum in your fingers. Yeah. The more you try to get it off, the worse it gets, and your mom hates it.
Well, Fred, I think Valerie's going to steal some of your sayings for her outreach book. Okay, so are there any more questions, comments?
I've got a question for
okay.
Will and Gabe. Is the sterile neutrino a good candidate to explain the 25% dark matter?
I would say from that recent paper.
Probably not.
It probably wouldn't.
Probably not. Oh yeah, but neutrinos, while there are a ton of them, fairly low mass. I think the better candidate for dark matter universe would probably be WIMPs, the weakly interacting massive particles, which exist at higher energy ranges, have much higher masses, and would basically, yeah, they're much harder to detect. Because because we would detect neutrinos fairly readily, sterile neutrinos would only exist as a transition point from the active neutrinos to their other flavors. So
this isn't one of those super heavy neutrinos?
No. Yeah, actually, that's one of the reasons why Fermilab is so useful, is because the lipid argon detector in ICARUS can detect at much lower energy levels.
Okay.
Yeah.
All right, well, if there are no more questions, let's thank all our speakers again.